Hello everyone, this is Sultanus Salihin. I'm here to present our project for neural network course. The project is titled DNN-Based Automated Diabetic Retinopathy Detection. Let me give you a very brief and very good understanding of what we did for our project. So, as a problem statement, the goal is to classify retinal images into diabetic retinopathy severity levels using CNN-based architecture. The dataset that we took is from a Kaggle competition, which was released in 2015, and it consists high-resolution retinal images having 5 DR severity levels from no DR, mild, moderate, severe, and proliferative DR. After doing exploratory data analysis, we noticed that there is a very vast class imbalance in the dataset. The total images are 36,000. So we did a stratified splitting to make sure for training, validation, and testing split, we maintain the 60%, 20%, 20% for all the class levels. Even though we have more images for class 0, we made the splitting in a way so that the balance is maintained throughout. And we also had different resolution side. That's why we did different types of pre-processing. Let's move on to the pre-processing. As part of the pre-processing, we took the original image, we cropped the image to remove the black borders. Then we did a pre-processing technique called CLACH, which is contrast limited adaptive histogram equalization. Then what it did was, if you see from the cropped images to the CLACH images, the retinal veins are more visible. The contrast is enhanced. That's why it's more adaptive for the perfect for the neural network to get it fed with. And then we resized all the images into 512 times 512 to remain the consistency. Then we tried a baseline model that we talked about in our update 1. We tried to come up with a new model from scratch, but it did not perform really well. We will talk about it in the evaluation plan. But for baseline model, we took a convolutional neural network. We had 3 layers followed by flattening layer, 1 dense layer, and the second dense layer. In between, we have dropout of 50%. And then the output layer would give us the 5 output classes. But then we explored a little bit. We did some literature review, and it turned out the efficient net and different versions of it actually can do very well in this kind of image-based classification. So as a backbone of this, as a backbone of this network, we took efficient net B0 as our backbone, and then we added a multi-head self-attention layer, and which has 4 different heads, and the network ends with 2 fully connected layers, which gives us 5 different classes. So why did we choose multi-head self-attention? Because while the efficient net would focus on local features, multi-head self-attention was able to focus on the global features as well within each of the images. So if we move on to the evaluation plan, if you can see the leftmost table, we can see for the baseline model, the accuracy and losses were a bit plateaued throughout the whole 10 epochs. But for RetinoNet, what we built from the backbone of EfficientNet, the RetinoNet performed really well in terms of accuracy. And the ROC AUC curve you can see here is for the baseline one. It did not perform well at all. But the last 3 curves here are the trained versus validation loss, trained versus validation accuracy, and trained versus validation cohort kappa. You can see from the loss that, and these are for the final RetinoNet, not the baseline one. You can see for the loss that after the 7th epoch, the loss actually has it gets better, and for the accuracy also it gets better. And for Cohen kappas, let me clarify what kappa is. You introduced a loss function which is called loss quadratic weighted kappa. It measures the agreement between predicted and actual ratings, which actually penalizes bigger mismatches more heavily. So if the network gets confused with class 0 with class 4, it penalizes the network more if the network gets confused with class 3 versus class 4. So that's how the Cohen kappa loss performed or calculated. And these are the final results for our RetinoNet. You can see the ROC curve for per class. For class 1, it does not perform that well, but for other 4 classes, it performed really well. And for the precision recall and F1 score, we can see the class page precision recall F1 score and also the overall test set evaluation matrix where we calculate accuracy, precision, recall, F1 score, and kappa score. The confusion matrix a bit confusing for us as well because for different classes it gets confused because for class 0 we had more data, more images. That's why it looks a bit distorted. And for prior work, we had previously have experience with CNN and by LSTM models and GAN-based work, but we did not particularly work with DR classification or medical image size. These are our references. Thank you so much.